Hi, in this lecture we will continue the reactions of alkyl halides, nucleophilic substitution reactions. This is the second part of the lecture. So, as you remember, in the previous lecture we are left at the nucleophile effect on SN2 reactions. Okay, let's start. As you remember from previous chapters, a nucleophile is generally a negatively charged or a neutral species having a lone pair, which we call it's a Lewis base. It can donate its electron pair. Okay, as we said, it can be either negatively charged or neutral, and they are Lewis bases. And from the previous chapters, you have seen that this is acetylate anion. It's a good nucleophile. It undergoes an SN2 reaction, and we can synthesize alkynes. Okay. Why do some reactants, or why do some nucleophiles react faster, and why some of them react slower? Or we can define it, why some nucleophiles are more nucleophilic, or some of them are less nucleophilic, or some of them are good nucleophile and the others are bad nucleophiles or weak nucleophiles. So we are going to see the effect of nucleophilicity in SN2 reactions. Here we have a table, and this table summarizes the effect of nucleophile on SN2 reactions. We have a reaction, we have a template reaction, we have a generic reaction in which we have the same substrate, which is bromomethane, and we are changing the nucleophiles. And here on this column we have 4, 6, 9 different nucleophiles, and they will each generate different products, substitution products, as here, and the same leaving group. And here, that's the relative rate of each reactions. What does it mean? This is the slowest reaction, and this is the fastest reaction. So, can we get some generalization with respect to identity or features of nucleophiles and reaction rate? Some of them are reacting faster than the other ones. Why they react? So can we get some generalization? So in this part we are going to see that one. Okay, so let's look at this slide. So we are going to see basically 3 effects. One is basicity. Basicity affects the nucleophiles, or like being a good base or being a strong base or being a weak base affect the reaction rate. Second, is there any generalization in periodic table or between bases or between nucleophiles that we can come up? So we are going to see that one in this table. So let's look at here. We say that nucleophilicity roughly parallels with basicity. Why it's roughly? Because basicity, or being basic, being less basic, being more basic, basically it's related to an atom's affinity towards hydrogen, right, or proton. But for nucleophilicity, generally nucleophiles have affinity towards electrophiles, and that electrophiles is carbon atom we have seen in this reaction. So that's the reason why it's not always parallel, but it's roughly. Let's look at for example, when you look at 2 bases that are known. For example, hydroxide is a known base, and acetate anion, it's a base, right? Which one is more basic? We know that hydroxide, because we know that hydroxide of sodium, potassium 1A are strong bases, right? But sodium acetate is a weak base, because acetic acid, the weak acid, and its conjugate base is acetate anion. So the first thing, if you are more basic, generally you are better nucleophile. How do we understand? Look at here. Hydroxide reacts 10 times and acetate 500 times with respect to water. And we can also compare the basicity of water and hydroxide. Water is weak base, hydroxide is a strong base. You see it's 10,000 times reacting faster if you are more basic. So that's the first effect. Second effect, we say that can we get some generalization in periodic table? For example, same group in periodic table 7a. Let's look at the nucleophiles in 7a. Cl and iodide. Which one is better nucleophile? Iodide is better nucleophile or reacts faster with methylene bromide than chloride, right? So why iodide is reacting faster than chloride? Because it's more basic, we can say, or why it's more basic, or why it can donate its electron, one-off electron pair easier, because if you compare the size of chloride anion and iodide ion roughly, so we know that when we go down in the 7a in periodic table, the size increases. Why? We add always from one period to another one more electron share, right? Electrons are successively becoming further away from the nucleus. So there are, let's say, 2 electrons will be donated from iodide to this methylene bromide. So these 2 electrons are tightly held in the chloride, but it's loosely held in iodide. Why? Because the distance between nucleophile and the last shell is greater for iodine. So as the size increases, we can also see in the 6a, for example, if you compare hydroxide versus sulfide, hydrosulfide is more basic or is more nucleophilic than hydroxide. Why? Because sulfur is larger than oxygen in terms of size. So, but we have to compare the same group. That's the keyword. Okay, then I think there was something about the charge. For example, water is a neutral nucleophile, and hydroxide the same nucleophile, oxygen and oxygen, but this is charged, right? So generally charged nucleophiles are better nucleophiles or more nucleophilic than uncharged ones. So these are the generalization. First one is more basic. If you are more basic, you are more nucleophilic. Don't forget this order sometimes can change if you change the solvents, if you change the substrate, if you change the experimental conditions, but more or less we will follow these guidelines. SN2 reactions we will see later. We will employ, or generally if we employ here aprotic solvents. That's the comparison. Okay, let's solve this question, and it will give us some more intuition. Okay, the first one is not related to like nucleophilicity, but it's an exercise for SN2 reactions and what are our nucleophiles we are going to see. So let's look at the problem. What product would you expect from SN2 reaction of 1-bromobutane with each of the followings? Let's write here 1-bromobutane. We have 4 carbon, 1, 2, 3, 4, and we have bromine leaving group. So we are reacting with nucleophiles. So I'm going to add here the nucleophiles. In the first case, we have sodium iodide. Iodide ion or anion is going to be our nucleophile, right? So what are we going to get? We are going to get, instead of bromobutane, we will get 1-iodobutane, right? So 1, 2, 3, 4, then this is iodine. Okay, then in the second one, what's the nucleophile? Potassium hydroxide ion, right? OH minus, let's put lone pairs. So what's going to be the product? This is butanol. You don't have to know the name. Here we have a molecule having carbon carbon metal bond. So basically you don't have to know at this level, but this part, because lithium is a metal, let's say this is not an ionic bond, but think of it's like an ionic bond, because we have here a metal non-metal bond, which is again here it has like a covalent character. But if you think the extreme case, if this is an ionic bond, lithium is going to be positively charged, this carbon is going to be negatively charged. So you can think of here the nucleophile is this HC carbon, and there is a carboanion, acetylate anion. So what's going to happen, instead of this, or instead of Br, we will have this group. So 1 2 3 4, and the nucleophile is this, it will be attached. So this is the product for this. And let's look at this one, D, ammonia. Let's draw it here, 3 hydrogens and lone pair, so it's basic. We know that ammonia is weak base, right? What's going to happen, it will attack this carbon and it will substitute Br, and you are going to get N, H, 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 and positively charged. Later on you will see, but if you have other bases around, so it can deprotonate the positively charged amine, and we can generate a neutral one, but just in this level you don't have to worry about it. Okay, let's look at the next question. The next question is 11.5. Which substance in each of the following pairs is more reactive as a nucleophile? Explain. Let's look at A. We have an amide ion, here an amine, right? So we know that same. So nitrogen, same nucleophile, 2-methyl. Here no hydrogen, there is one hydrogen. So basically like hydroxide versus water. So negatively charged nucleophiles are better or more nucleophilic than neutral ones. Let's look at here. Here we have boron, we have nitrogen, we have three methyl group, 3 methyl group, same. So same row, right? In periodic tables, I think this is second period. So nitrogen has a lone pair, and boron doesn't have, because boron is an exception to octet rule also, right? For that reason, it has 6 electrons around, and it's Lewis acid. So it's reactive with Lewis bases, so it's not a base basically. So we know that amines are base, but you can think this way, like boron, nitrogen is more electronegative, so it's going to be like, it has also a lone pair, so it's going to be more basic. So I'm going to choose this one. Water versus hydrogen sulfide. We remember, right, the same group, 6A, oxygen and sulfur. Sulfur has larger atomic radius. For that reason, electrons on the last shell loosely held. So it's more basic, or let's not say basic, but it's more nucleophilic. Here again, we don't say like more basic, but again, nucleophilic, more nucleophilic. We know that boron is a Lewis acid, but nitrogen or amines or ammonia, they are Lewis bases. So you have to know a little bit which one is base, which one is acid for the second part. Okay, then let's look at the next effect. The next effect is the leaving group. So what was our reactions? The nucleophilic substitution reactions, right? So I'm going to write a generic nucleophilic substitution reaction, or in this case this is SN2 reaction. We have a nucleophile, lone pair negatively charged. Then here we have a leaving group. I'm going to say leaving group not X, not a halogen, but as L. It depicts better. Okay, so what happens? Nucleophile attacks the electrophilic carbon, leaving group leaves. So in the transition state we have this planar complex. This is nucleophile, this is leaving group. So nucleophiles loses its negative charge, and leaving group starts taking these 2 electrons on the sigma bond, and it has partial negative, and so then what's going to happen as the reaction finishes? Nucleophile will be attached here. Inversion plus leaving group generally leaves with a negative charge. Okay, so what I said here, leaving group is expelled with a negative charge in most SN2 reactions. Okay, so the best leaving groups. So we can categorize leaving groups: good leaving groups, bad leaving groups, best leaving groups, worst leaving groups. So which are best leaving groups or which are worst leaving group? So if that particular leaving group is reacting faster, let's say that we are changing here just the leaving group. We are keeping nucleophile, solvent, everything the same. Only we are changing the leaving group and we are comparing this. So this is the best leaving group because it reacts 60,000 times than this one. So why this is a best leaving group? Why these are the worst leaving group? Let's see the energy diagram for SN2 reactions. Let's say we have an hypothetical energy diagram. With a good leaving group or with a bad leaving group, we are going to have two different energy curve or energy profile. The black one, the black curve is with the worst leaving groups, or like not good leaving groups, let's say, and the red one, which reacting faster, the substrates with good leaving groups. So why is that case? Because as you see, the reactants, they have almost same energy, but the products, or rate depends on the activation energy, right? The good leaving groups, they have lower activation energy. Bad leaving groups, they have, or the reaction with the bad leaving groups, they have higher activation energy. Why the good leaving groups, the substrate with the good leaving groups, have lower activation energy? Because the transition states, they have, their transition states are more stable. Why it's more stable? You can see that even in products we have a negative charge, right? Or during the transition state, the leaving group is leaving with a partial negative charge, but it will be a full negative charge when the reaction finishes. Okay, so there is a negative charge around leaving group. So whoever stabilizes that negative charge will be good leaving groups. So who are good leaving groups then? Generally weak bases. So for example, this is a base, right? It's a Lewis base, it's a lone pair, it can donate. So if you are a weak base, what does it mean? You are more stable, you have less energy. So who can have less energy? Whoever can stabilize the negative charge, it will be more stable and it will be weaker base, and the reaction will be faster. So if you look at here, generally, let's try to compare same groups. Iodide is the best leaving group in 7A. If you compare fluorine, chlorine, bromine, iodine, why iodine is the best leaving group? Again, iodide is the weakest base. If you compare, fluoride is the strongest base. Or why? Because iodide is the largest in terms of size. What happens when your size is bigger? Because again, I'm going to compare here fluoride minus and iodide minus. Here there is a net negative charge, right, on this region or in this area or in this volume, and there's a negative charge in this small volume. So this negative charge will be spread over a larger volume, and this negative charge on fluoride will be on a smaller volume, in a smaller volume. So we can spread this negative charge into more surface or more volume, and this will be more stable. So don't forget, if you can spread your charge more you will be more stable. Why? Because you cannot concentrate your negative charge or your electrons, and you cannot act as a good Lewis base. So for that reason, in the same group, if the size increases, you become better leaving group. Okay, then let's look at these parts. Why hydroxide, amide, or alkoxide ions are worst leaving groups? Because they are very strong bases. You know, sodium hydroxide, you know, sodium amide, you know, sodium sodium methoxide, sodium ethoxide. They are very powerful bases. That's the reason why they are not good leaving group. Okay, I'm going to stop here, so we will continue in part 3, the leaving group ability. Thank you so much.